Welcome viewers to the lecture series on integral equation under NPTEL courses. In last lecture we have considered the Fredholm integral equation of second kind with non-homogeneous term, and we have discussed in case of separable or degenerate kernel how the given Fredholm integral equation can be converted into a system of linear equation. And briefly we have discussed that depending upon the existence of solution of the system of linear equations, we can find out solution to the given Fredholm integral equation. In this lecture, first we consider one more example, because example we discussed in the type, because summation p r x q r s d s for the selected problem contains only one term, that is P1 and Q1 term. So, in this lecture we can start with this example that we have to solve this equation y x is equal to x plus lambda integral minus pi to plus pi x cosine s plus s square sin x plus cosine x sin s y s ds. So, with the notation we have discussed in the last lecture, here P1 x is equal to x, P2 x this is equal to sin x, P3 x this is equal to cos x, and Q1 s this is equal to cos s, Q2 s this is equal to s square, Q3 s this is equal to sin s, and therefore, the kernel given kernel k x comma s is nothing but sigma r runnings from 1 to 3 p r x q r s. So, now we can write the integral equation into this format, that is y x equal to x plus lambda x integral minus pi to plus pi cos s y s ds plus lambda sin x integral minus pi to plus pi s square y s ds plus lambda cosine x integral minus pi to plus pi sin s y s ds, and that is equal to x plus lambda x y 1 plus lambda sin x y 2 plus lambda cos x y 3, where this y 1 stands for minus pi to plus pi cos s y s ds, y 2 this is equal to minus pi to plus pi s square y s ds, and y 3 this is equal to minus pi to plus pi sin s y s ds. So, as we have discussed in the last lecture, that now we have to multiply this expression, that is y x equal to x plus lambda x y 1 x plus lambda sin x y 2 plus lambda cosine x y 3 by cosine x, x square and sin x respectively, and then we have to integrate from minus pi to plus pi in order to constitute the system of linear equations for y 1, y 2, y 3. So, we can do that. Alternatively, we can think about that y s, this is equal to s plus lambda y 1 s plus lambda y 2 sin s plus lambda y 3 cosine s. And with this definition for y s, we can substitute this y s into the definition for y 1, y 2, y 3 in order to construct the system of linear equations. So, therefore, from the definition for y 1, we can write y 1 equal to integral minus pi to plus pi s cosine s plus lambda y 1 s cosine s plus lambda y 2 sin s cosine s plus lambda y 3 cosine square s ds. And from here we can write this is equal to 1 plus lambda y 1 minus pi to plus pi s cosine s ds plus lambda y 2 integral minus pi to plus pi sin s cosine s ds plus lambda y 3 integral minus pi to plus pi cosine square s ds. Now, first two integrals vanishes as s cosine s is an odd function, sin s cosine s is also an odd function, and in both the cases limit is from minus pi to plus pi. So, both of them is equal to 0, and the last integral can be written as lambda y 3 integral 0 to pi 1 plus cos 2 s ds, because minus pi to plus pi can be converted into 2 0 to pi, and then 2 cos square s is nothing but 1 plus cos 2 s, and after integration we will be having lambda y 3 s plus sin 2 s divided by 2 limit from 0 to pi, and therefore, this will results in this is equal to lambda y 3 pi. This will be the result. So, for the first part, and then for the second expression y 2, this is equal to integral minus pi to plus pi s square y s ds, and this is equal to integral minus pi to plus pi, substituting the expression for y s, we can find this is s cube plus lambda y 1 s cube plus lambda y 2 s square sin s plus lambda y 3 s square cosine s ds. And again here s cube plus lambda y 1 s cube ds, this will be 0 because it is odd function, and s square sin s is also an odd function. So, therefore, we are left with the last integral, that is minus pi to plus pi lambda y 3 s square cosine s ds, and this will be equal to 2 lambda y 3 integral 0 to pi s square cosine s ds, and after integrating by parts we find 2 lambda y 3 s square sin s plus 2 s cosine s minus 2 sin s limit 0 to pi, and ultimately we will be having only one non-zero term, that is from 2 s cosine s when evaluated at s equal to pi. So, substituting these limits, upper lower limits and upper limits, this will result in minus 4 lambda pi y 3, and finally, for y 3 this is equal to integral minus pi to plus pi. You can recall the definition, this is minus pi to plus pi sin s y s ds. So, this is sin s y s ds, and substituting the expression for y s, this reduces to minus pi to plus pi s sin s plus lambda y 1 s sin s plus lambda y 2 sin square s plus lambda y 3 sin s cosine s ds, and this will be equal to 2 into 1 plus lambda y 1 integral 0 to pi s sin s ds, because s sin s is an even function and limit is from minus pi to plus pi, then plus 2 lambda y 2 integral 0 to pi sin square s ds, and last integral is again equal to 0 because sin s cosine s is an odd function. And after evaluating this integral, we can find 2 into 1 plus lambda y 1, then limit minus s cosine s plus sin s 0 to pi plus lambda y 2 s minus sin 2 s divided by 2 limit 0 to pi, and this will results in 2 pi plus 2 lambda pi y 1 plus lambda pi y 2. This is the result. So, now if we collect all the equations that we have obtained, so from first we have obtained y 1 equal to lambda pi y 3, then y 2 equal to minus 4 lambda pi y 3, and finally here y 3 equal to 2 pi plus 2 lambda pi y 1 plus lambda pi y 2. So, finally, we can write down the system of equation as y 1 minus lambda pi y 3, this is equal to 0, then y 2 plus 4 lambda pi y 3, this is equal to 0, and minus 2 lambda pi y 1 minus lambda pi y 2 plus y 3, this is equal to 2 pi. So, therefore, the coefficient matrix is consisting of these coefficients, that is 1 0 minus lambda pi, then 0 1 4 lambda pi, and minus 2 lambda pi minus lambda pi 1. So, therefore, we have unique solution if this determinant is non-zero. Now, if we calculate this determinant, that is determinant 1 0 minus lambda pi 0 1 4 lambda pi minus 2 lambda pi, then minus lambda pi 1, this determinant will be equal to 1 plus 2 lambda square pi square. So, just for example, if we assume lambda is real, so therefore, we can say this quantity is always not equal to 0, and therefore, for all values of lambda, this system of equation is uniquely solvable. Now, without going towards the matrix inversion method or Cramer's rule to solve this system of linear equation, directly from this equation you can find y 1, that is equal to lambda pi y 3, and y 2, this is equal to minus 4 lambda pi y 3, and substituting these two expressions in the third equation, we can then solve for y 3, and solving we get y 3 equal to 2 pi divided by 1 plus 2 lambda square pi square. So, with this y 3 immediately we can find y 1, this is equal to 2 pi square lambda divided by 1 plus 2 lambda square pi square, and y 2 this is equal to minus 8 pi square lambda divided by 1 plus 2 lambda square pi square. And therefore, with these expressions for y 1, y 2 and y 3, we can find the solution for the given problem, that is y x is equal to x plus 2 lambda pi divided by 1 plus 2 lambda square pi square, this multiplied with lambda pi x minus 4 lambda pi sin x plus cosine x. So, this is the solution. That means, actually we are substituting these expressions for y 1, y 2, y 3 into the first expression, where we have obtained y x is equal to x plus lambda x y 1 plus lambda sin x y 2 plus lambda cosine x y 3. So, substituting these values we can get the general solution. Now, we discuss different possible situations for the solutions of system of linear equation what we have derived in the last lecture, and through which we can understand what is the concept of eigenvalues and eigenfunctions associated with a linear integral equations, that is Fredholm integral equations. So, for that purpose we recall that the given integral equation y x is equal to f x plus lambda integral a to b k x comma s y s ds, where k x comma s is a degenerate or separable kernel which is of the form sigma r runnings from 1 to n p r x q r s can be converted into a system of linear equations which is given by I n minus lambda a n cross n, these multiplied with y, that is equal to capital B. So, that means existence of solution of the system of linear equation where y is the unknown column vector with n components y 1, y 2, y 3 up to y n, we can discuss the different possible situations for the solutions of the Fredholm integral equation. So, first of all you can recall this B was a matrix of the form some constants B 1, B 2 up to B n, and this B 1, B 2 up to B n, these are nothing but the integral a to b f x q r x dx. So, therefore, if we assume the first case, if we assume that f x equal to 0, if we assume f x equal to 0, then all the b j's are identically equal to 0, and therefore, this B is nothing but an n cross 1 column vector, and once n cross 1 column vector is null column vector is B, and therefore, we will be having the system of linear homogeneous equations I n minus lambda a n cross n multiplied by y, that is equal to theta n cross 1, and whenever f x equal to 0, then the given Fredholm integral equation of second kind is a homogeneous Fredholm integral equation of the second kind, and therefore, this system of equation admits solutions y is equal to theta n cross 1, this is the trivial solution, and whenever y 1, y 2 up to y n, all these quantities are identically equal to 0. So, therefore, y x equal to 0 is a solution to the given Fredholm integral equation, which is a homogeneous equation because f x is equal to 0. Now, if it happens that I determinant I n minus lambda a n cross n, this is not equal to 0, then unique solution for this homogeneous system of linear equation is y equal to theta n cross 1, and therefore, from here you can verify that y x equal to 0 is the only solution for this integral equation y x is equal to integral a to b k x comma s y s ds. So, this is the unique solution and which is identically equal to 0. So, therefore, this homogeneous Freedom integral equation admits only the trivial solution. Next, we consider the case that determinant I n minus lambda n cross n, this is equal to 0. Now, what is happening here? If this is equal to 0, then at least one of the y j can be assigned some arbitrary non-zero value. If this determinant is 0, then we can assign at least one of the y j arbitrary non-zero quantity, and then accordingly remaining y j's can be obtained in terms of this y j, and this choice of arbitrary value for y j as it is arbitrary. So, therefore, it actually admits infinitely many solutions of the integral equations. So, this is very much important point. If this determinant I n minus lambda a n is equal to 0, then we have infinitely many solutions of the integral equations. Now, the value of lambda for which this determinant is 0, value of lambda for which this determinant I n minus lambda a n cross n, this is equal to 0, these are known as characteristic values or eigenvalues of the Freedom integral equation, and any non-trivial solution of the homogeneous integral equation associated with the eigenvalue lambda, those are actually called the eigenfunctions. So, therefore, any non-trivial solution solutions of y x is equal to lambda integral a to b k of x comma s y s ds are called eigenfunctions. So, this is the definition or concept associated with the eigenvalue and eigenfunction of an integral equation. Now, the point is that if m of the constants, that means among these y 1, y 2 up to y n, among these if m can be assigned to arbitrary values for a given particular value of lambda, then we can find m linearly independent eigenfunctions that can be obtained. So, that means depending upon the how many of these y 1, y 2 up to y n can be assigned as arbitrary constant, then in the solution those p 1 x, p 2 x up to p n x, they will be appeared, and those will be actually eigenfunctions corresponding to this arbitrary choice of y 1, y 2 up to y n, for which these y j's are actually non-zero. Of course, we will explain this idea with help of a particular example. So, up to this we have considered f x equal to 0. Next, we consider that f x this is not equal to 0. If f x not equal to 0, still there is a possibility that we can have system of linear homogeneous equations corresponding to that I n minus lambda a n cross n y is equal to b, and the point is that if f x is orthogonal to all q 1 x q to x up to q n x for x belongs to closed interval a comma b, then we will have the equations, that is I n minus lambda a n cross n multiplied by y, that is equal to theta n cross 1. So, therefore, as we have discussed earlier, there will be two possibilities. Number 1, that determinant of I n minus lambda a n cross n, this is not equal to 0. Now, if this is not equal to 0, then the system of linear equations I n minus lambda a n cross n times y, that is equal to theta n cross 1, admits only one solution, that is y equal to theta n cross 1. But in this case, we will be having a non-trivial solution, that is given by y x is equal to f x. So, y x equal to f x is the non-trivial solution, for the equation y x is equal to f x plus lambda integral a to b k of x comma s f s d s. And the case when we will be having this I n minus lambda a n cross n, this determinant equal to 0, then we can find the corresponding eigenvalues, and therefore, we will be having the eigenfunctions, and in that case solution will be the sum of f x and the scalar multiple of eigenfunctions of the associated problem. And finally, if we consider that at least one of integral a to b f x q m x is non-zero, so that means we are assuming b not equal to theta n cross 1. If this happens, then we will be having unique solution to the Fredholm integral equation whenever determinant of I n minus lambda a n cross n, this is not equal to 0. So, therefore, for b not equal to theta n cross 1, we will be having unique solution to the Fredholm integral equation if this determinant does not vanishes. And in case if this happen, that I n minus lambda a n cross n, this is equal to 0, then system of equations will be either inconsistent, and if the system of equations are inconsistent, there does not exist any solution, or they are redundant. In case of redundant equation, we will be having infinitely many solutions for the given problem. So, this is all about discussions regarding the nature of solutions of the Fredholm integral equation associated with the nature of the determinant I n minus lambda a n cross n, and whether the matrix B is a null matrix or it is a non-null matrix. Now, in the last lecture, we have obtained the resolvent kernel of a integral equation. In this case, we are again going to address the same problem, and based upon this discussion, we can find out the eigenvalues, eigenfunctions, and we will be able to illustrate all these ideas with help of the same example. So, the problem is y x this is equal to f x plus lambda integral 0 to 1 minus 3 x s y s d s. And just for your information, you can get this example in the Hildebrandt's book on mathematical methods, or any other book like Wazwa's book or Kanowal's book. This is a very famous example. You can find it in several places on the book of integral equations. So, now we are going to discuss the solution of this particular problem depending upon various natures of f(x), that means whether it is 0 or it is non-zero or whenever it is orthogonal to the functions associated with the given problem. So, first of all we can rewrite this equation as f(x) plus lambda integral 0 to 1 y s ds minus 3 lambda x integral 0 to 1 s y s ds, and defining y1 is equal to integral 0 to 1 y s ds and y2 is equal to integral 0 to 1 s y s ds. We can write y x, this is equal to f x plus lambda y 1 minus 3 lambda x y 2. So, this is the expression for y x. Now, in this expression, that is y x 1 is equal to integral 0 to 1 y s ds. Substituting this expression for y s, we can find this is equal to integral 0 to 1 f s ds plus lambda y 1 integral 0 to 1 ds minus 3 lambda y 2 integral 0 to 1 s ds. So, this will be equal to integral 0 to 1 f s ds plus lambda y 1 minus 3 by 2 lambda y 2, and therefore, from here we have the first equation of the system of two linear equations, that is 1 minus lambda y 1 plus 3 by 2 lambda y 2, that is equal to integral 0 to 1 f s ds. So, this is the first equation, and for the second y 2 is equal to integral 0 to 1 s y s ds, and after substituting the expression for y s and evaluating the integral, you can find 0 to 1 s f s ds plus lambda by 2 y 1 minus lambda y 2, and from there we can write minus lambda by 2 y 1 plus 1 plus lambda y 2, this is equal to integral 0 to 1 s f s ds, and therefore, the determinant, that is I 2 minus lambda a 2 cross 2, this is equal to the determinant 1 minus lambda 3 by 2 lambda, then minus lambda by 2 and 1 plus lambda. So, this is equal to, after simplification, will be comes out to be 1 by 4 minus lambda square. So, in this case we can say that unique solution exists whenever lambda not equal to plus minus 2. If lambda not equal to plus minus 2, so whether f x equal to 0 or f x not equal to 0, we can find unique solution for the given Fredholm integral equation. Now, and the solution can be obtained by substituting the expressions for y 1 and y 2 by solving these two equations, either in the form involving integral 0 to 1 f s ds and 0 to 1 s f s ds, and otherwise if f s is given. So, evaluating both these integrals, that is 0 to 1 f s ds and 0 to 1 s f s ds, you can find out uniquely y 1 and y 2, and then substituting into the required expression, that is y x equal to f x plus lambda y 1 minus 3 lambda x y 2, you can find out the unique solution for the given problem. Now, we consider the case that if f x equal to 0, if f x equal to 0, then for lambda not equal to plus minus 2, y x equal to 0 is the only solution. is the only solution. So, therefore, if f x equal to 0 and lambda not equal to plus minus 2, then given problem admits only trivial solution. And now we can consider the cases, that is values of lambda equal to first 2 and then minus 2. So, we have this system of equations. You can recall that 1 minus lambda y 1 plus 3 by 2 lambda y 2, that is equal to integral 0 to 1 f s ds and minus lambda by 2 y 1 plus 1 plus lambda y 2, this is equal to integral 0 to 1 s f s ds. So, here if we assume that lambda equal to 2 and f s not equal to 0, above system of equation reduces to y 1 minus 3 y 2, that is equal to minus integral 0 to 1 f s ds and y 1 minus 3 y 2, that is equal to minus integral 0 to 1 s f s ds. So, these are the two expressions we will be getting when we substitute lambda equal to 0 and with the assumption that f x is not equal to 0. So, with f x not equal to 0, we will be having this expression. Now, above two equations, that is y 1 minus 3 y 2 equal to minus integral 0 to 1 f s ds and y 1 minus 3 y 2 equal to minus integral 0 to 1 f s ds, these are incompatible unless integral 0 to 1 f s ds, this is equal to integral 0 to 1 s f s ds. So, actually that implies integral 0 to 1 minus s f s ds, this is equal to 0. So, if this condition does not hold, that is integral 0 to 1 minus s f s ds not equal to 0, then the system of equations are incompatible and therefore, there does not exist any solution. Similarly, for lambda equal to minus 2 and f x not equal to 0, we will be having the system of equation reduced to y 1 minus y 2, that is equal to 1/3 integral 0 to 1 f s ds, and from the second y 1 minus y 2 is equal to integral 0 to 1 s f s ds, and in this case the system of equations are incompatible unless integral 0 to 1 minus 3 s f s ds, this is equal to 0. And if this condition holds, that is 0 to 1 minus 3 s f s ds, then the system of equations actually redundant, because in this case both this equation can be reduced to a single equation. So, now the case when f x is equal to 0, if f x equal to 0 and lambda not equal to plus minus 2, then y x equal to 0 is the only solution that we have discussed earlier also. And next we can try to calculate the eigenfunctions associated with the eigenvalues plus minus 2 whenever this f x equal to 0. Now, for lambda equal to 2 and f x equal to 0, both this equation can be reduced to y 1 minus 3 y 2, this is equal to 0. And then from the expression, that is y x is equal to f x plus lambda y 1 minus 3 x y 2 with the substitution, that is f x equal to 0 and y 1 equal to 3 y 2, we can find this is equal to 2 times 3 y 2 minus 3 x y 2. So, this is equal to 6 y 2 times 1 minus x. Now, we can choose y 2 arbitrary quantity, and accordingly y 1 will be also the arbitrary quantity, and therefore, 6 y 2 can be written as alpha times 1 minus x. So, therefore, this 1 minus x actually eigen function associated with the eigenvalue 2 of the homogeneous Freedom integral equation. And proceeding in a similar manner, we can find that y x is equal to beta times 1 minus 3 x for lambda equal to minus 2, where beta is any arbitrary non-zero quantity, and therefore, we can say that 1 minus x and 1 minus 3 x, these are eigen functions corresponding to the eigenvalues lambda equal to 2 and lambda equal to minus 2 respectively. And finally, you can check that this lambda times y 1 minus 3 x y 2, this can be written in terms of linear combination of these two functions, that is 1 minus x and 1 minus 3 x, because this can be done, that this is equal to delta 1 times 1 minus x plus delta 2 times 1 minus 3 x. If we choose delta 1 equal to 3 lambda by 2 times y 1 minus y 2 and delta 2, this is equal to lambda by 2 3 y 1 minus y 2. So, from here you can see that always this lambda times y 1 minus 3 x y 2 can be written as lambda delta 1 times 1 minus x and delta 2 times 1 minus 3 x. So, these 1 minus x and 1 minus 3 x, they are eigen functions of the associated problem, and therefore, the solution, that is y x, this is equal to f x plus lambda into y 1 minus 3 x y 2 is nothing but the sum of this given function f x and linear combination of the eigen functions, that is delta 1 into 1 minus x plus delta 2 into 1 minus 3 x. So, that we have claimed in case during the theoretical discussion on this problem, that whenever this lambda is taking the value plus minus 2 and f x is non-zero. So, therefore, this solution can be written as the linear combination of the eigen functions summed with the given functions f x. For lambda equal to 2, no solution exists if 0 to 1 1 minus s f s d s, this is not equal to 0. If this quantity is not equal to 0, that is the integral 1 minus s f s d s not equal to 0, then there does not exist any solution, and in case f s is orthogonal to 1 minus s within the range 0 to 1. So, that means integral 0 to 1 1 minus s f s d s, this is equal to 0. In that case, we can write y 1 is equal to 3 y 2 minus integral 0 to 1 f s d s. This is the result will come up for y 1, and in that case we can write down the solution of the given problem, that is y x equal to f x plus lambda y 1 minus 3 x y 2, and substituting the expression for this y 1, we can write f x plus 2 into 3 y 2 minus integral 0 to 1 f s ds minus 3 x y 2, and ultimately this is coming out to be f x minus 2 integral 0 to 1 f s ds plus alpha times 1 minus x, because 6 y 2 minus 6 x y 2 can be clubbed into 6 y 2 times 1 minus x, and 6 y 2, this y 2 is an arbitrary quantity in this case for lambda equal to 2, then 6 y 2 can be written as arbitrary quantity alpha, and hence the solution is given by y x is equal to f x minus 2 integral 0 to 1 f s ds plus alpha times 1 minus x. And in the case in this case you can easily verify that any non-zero values of alpha you can get an infinite set of solutions for the given problem. For example, substituting alpha equal to 1, 2, 3, 4 and so on, in all the cases you will be having y x equal to f x minus 2 integral 0 to 1 f s ds plus this either 1 into 1 minus x or 2 into 1 minus x, this as the solution of the given equation. So, in this case we will be having infinite number of solutions, and for lambda equal to minus 2, and if this condition is satisfied, that is 0 to 1 minus 3 s f s ds, this is not equal to 0, then no solution for the given equation, then there does not exist any solution for the given equation. And for lambda equal to minus 2, we can again find the solution for the given problem in a similar fashion. That means, if we find that integral 0 to 1 minus 3 s this f s ds, this is equal to 0, then we can find infinitely many solutions for the given problem. And in this case the solution can be obtained as y x is equal to f x minus 2/3 integral 0 to 1 f s ds plus beta times 1 minus 3 x, where beta is an arbitrary constants. So, this clearly shows under different possibilities, that is whenever f x is identically equal to 0, then we will be having system of linear homogeneous equation, and depending upon values of lambda we can have either unique solution or no solution, and in case f x equal to 0 and that determinant, that is I n minus lambda a n cross n not equal to 0, we will be having the trivial solution, that is y x equal to 0 is the only solution, and in case that determinant is non-zero, then we will be having infinitely many solutions. And another point that you have to keep in mind, that only f x equal to 0 will not be corresponding to the system of linear homogeneous equations, that is I n minus lambda a n cross n y equal to theta n cross 1. In case the non-homogeneous part of the given Fredholm integral equation f x satisfies the condition that it is orthogonal to each of the functions q 1 x, q 1, q 2 x up to q n x within the interval a comma b, then still we will be having a system of linear homogeneous equation, and depending upon the nature of the determinant, whether this is equal to 0 or this is non-zero, we will be having the case of unique solution or no solution. And with this example we have illustrated that in some situations when eigenvalues and eigenfunctions exist for the given problem, then solution to the given Fredholm integral equation will be the sum of f x plus linear combination of the eigenfunctions, and all these items will be addressed in terms of Fredholm theory, where this Fredholm theory relates with the solution of a Fredholm integral equation with the resolvent kernel for the Fredholm integral equation, and there we can discuss the same thing in terms of the 3 Fredholm theorems. So, in this lecture I can stop at here. Next 2 lectures will be on 3 theorems of Fredholm and Hilbert-Smith theory, those are related with the Fredholm integral equation. Thank you for your attention.